So now I will proceed with my registered paper, my presentation titled A Geometric Procedure for Computing Differential Characteristics of Multiphase Electrical Signals Using Geometric Algebra. But firstly, I must confess that I discovered the beauty of geometric algebra in the summer of 2018 while reading the work of Dr. Castro Nunez, a Colombian power engineer who works for the AECO, the Alberta Electric System Operator in Canada. And because of my long-standing interest in mathematics, I immediately fell in love. Fortunately, after several readings of his PhD thesis, I was able to correctly understand how he applied geometric algebra to the study of power theory and in electric system, but it was neither simple. This contrasts with the first time I heard about geometric algebra in electrical system in 2008, after Professor Bravo and Professor Castilla from the University of Seville. They published a paper in IEEE transaction on circuit and systems. The problem was they used a more intricate version of geometrical algebra that was impossible for me to digest. Specifically, they used geometric algebra over complex numbers. So regrettably, I feel that, well, in somehow, something here. Where's my mouse? Yeah, but I need the mouse. What is? No. I don't know where is the mouse. Oh, here, yeah, it was in the extant version. Yeah. So, so I said that I felt that in a way I lost 9 years of my research career. But anyway, I consider myself a lucky person to have finally discovered this topic and to be able to apply to electrical system. I consider to be an exceptional tool for electrical engineers, and moreover, it can manage to explain previously unsolved phenomena, as I showed you in a minute, some minutes ago. For example, the concept of geometric apparent power, the reactive power and the distortion power, which is a new concept based on the geometric algebra approach. For all these reasons, I would like to express my public thanks to all of you as representatives and members of the community of geometric algebra that makes possible a better understanding and development of geometric algebra ideas. In particular, I would like to thank Professor David Hastings for his tenacity and willpower in persevering with his ideas all these years. So thank you very much. And well, after these words, I will present my work. These are the goals of the presentation. The first one is to understand the concept of frequency in multi-phase systems. We use geometric algebra and differential geometry for this task. And frequency is something that all of us are aware of, something that repeats from time to time. It is easily understood for individual signals, but this is not the case for systems where multiple signals are considered as a whole, like in multi-phase power systems. So we will a special curve in an Euclidean space using voltage or current, it depends, what we call electrical curve. And by studying the differential geometric properties, we end up by building the Darboux bivector, which encodes the invariance of the curve, closely related to the traditional concept of frequency. Finally, we show how the instantaneous frequency, the frequency associated to an instant of time, can be intimately linked to this Darboux bivector. And the outline of the presentation is as follows: a brief introduction to the problem, the definition of electrical curves, where we show some interesting ideas about the relationship between the time as a parameter for a curve and the arc length. This is important to compute the local orthogonal frames like the well-known Frenet-Ferret frame. Then we move to the idea of how geometric frequency is embedded in the Darboux bivector and its plates. Some examples are provided to show the application of the method to electrical circuits, and finally some conclusions are drawn. Okay, some disclaimer. This presentation is created by an electrical engineer, so it's intended to mix it a wider audience, so not designed specifically for mathematicians. And basic concepts of geometric algebra are used in this presentation, mainly vectors and bivectors. There is no need to use more advanced concepts in this case. Okay, let's start with the introduction. Why the interest in power systems? Yeah, well, I think that everyone is aware of the crucial role of electrical systems in general and power system in particular in our society. So in this regard, the energy is delivered from generators to end user using multi-phase circuits. So they must be analyzed in terms of a multi-dimensional objects. And yes, the voltage and frequency are essential variables in every power system. For example, for stability purposes, so we need better tools to analyze the dynamics of our system in terms of transient disturbances that can potentially affect the grid. We also need a better understanding of the underlying meaning of some parameters. This is the case for the instantaneous frequency. This is a dispute and controversial concept. So how the repetition of something can be considered at a specific time. For this, some assumptions are made, like considering the signal a sinusoidal one, and apply quadrature methods to extract the instantaneous phase and amplitude, like, for example, the Hilbert transform does. To shed some light on this task, a new geometrical interpretation of frequency has been proposed recently by Professor Milano of the University of, I can't remember the name, a university in Ireland. Specifically, he proposed to deal with three-phase system using geometric invariance of the voltage curve. So we propose in our work to generalize the concept of frequency to an arbitrary number of phases by applying geometric algebra and differential geometry. Okay, we define an electrical curve as an n-dimensional Euclidean space curve generated by voltage and current measurements. So the process starts with uniformly sample multiphase and periodic voltage or current signals. In this case, this is a voltage. These values are BI key, where I is the phase index and the from 1 to n, and key is the sample index, so for that time instant. These samples are then interpolated to build a continuous curve to compute its differential geometry characteristics based on the derivatives of the curve. These samples are then, the result is a continuous curve, Bi of t. And in this figure, we show the representation of two arbitrary voltages, V1 and V2, starting from the samples, V1, V2, V3. So we can interpolate these samples and build a continuous curve based on some arbitrary interpolation method. Finally, we use these continuous waveforms as coordinates of an n-dimensional vector Bt. Vector V describes a curve in a space as shown in this figure. It is shown in an example of a three-phase under three-dimensional system. So the vector B is observed at two different instant time, t0 and t1. In our case, the time t will be the parameter on which the curve depends, and we will usually vary between 0 and a multiple number of the period of the system, usually 20 milliseconds for European networks and 16.6 milliseconds for American networks. So it is interesting to note that the curve B can be expressed as by a reparametrization of the t parameter. Usually it is interesting to do it as a function of the parameter S, or arc length. The definition is given by the following expression. So yes, we integrate the velocity of the curve, so we obtain the arc length. As we can see, S as a function of t indicates how far the curve has been traveled when the parameter t varies, while t as a function of S indicates how much time has elapsed when a certain distance has been traveled along the curve. The computation of the curve derivatives is of utmost importance in order to obtain the invariance of the electrical curve. Therefore, to study the electrical properties of the system. So these derivatives can be considered as a function of the parameter of t or S. So understanding the relationship between them is crucial for our development. So firstly, the first four derivatives of the arc length parameter are shown here as a function of the vector b and its derivatives. This is because the natural representation of the voltages is in the time domain, for sure, a function of time. In this way, by means of basic rules of differentiation, we can set the derivatives of the vector b with respect to arc length as a function of the derivatives with respect to the t parameter. Yeah, as can be seen, the relationship between, the relationship between the time derivatives and arc length derivatives is algebraically complicated, as the order of the derivative is increasing. So they are not as simple as the first derivative. So it's interesting to know that. And yeah, here we show the norm of these derivatives, b dot and b double dot. Here they're shown again for clarity along the orthogonality property among v dot and b double dot. The unit speed property is a logic consequence of choosing the arc length parameterization in contrast to the original t parameter. And the expression for the norm of the double dot is a bit more elaborated. It matches the value of the first curvature coefficient, also known simply as curvature. All the computation performed for the time derivatives are based on arc length will now be used to find the local reference frames at each point along the curve. As we will see later, this frame describes the dynamic properties of the curve and therefore of the electrical system they represent. So the figure shows a curve B and a point P to which we want to attach a local reference frame that describes the local geometrical properties. One way of obtaining this type of frames is through the derivatives of the curve. For this, we use an orthogonalization procedure such as Gram-Schmidt. The result is a system of orthogonal vectors attached to each point of the curve that evolve in time along with it. These vectors can be orthonormalized, of course, to obtain an orthonormal frame. Perhaps the best known then is the Frenet-Serret frame, which is discussed next. So the Frenet-Serret equations were formulated for 3 dimensions by Jean-Frédéric Frenet and Joseph Alfred Serret, and generalized to higher dimensions by Camille Jordan in the 19th century. They describe some dynamic properties of moving objects along the curves in a space by establishing the relationship between an orthonormal frame and its derivatives that also moves along the curve. These equations are shown here for convenience, along with the coefficients kappa I, which are known as curvature coefficient with n the number of dimensions. Yeah, these coefficients can be easily computed by performing the inner product between the basis vectors I plus 1 and EI dot. But well, we can use a new alternative expression, which is simple to compute, known here as the Gluck formula. Note that these curvature coefficients depend explicitly on the arc length, but can also be derived for the t parameter by the implicity dependency of vectors u on the time derivative of the voltage vector b. Yeah, for engineering purposes, it's more convenient to use a scale version of the curvatures. The scale factor is S prime, which is the velocity of the curve. So we call that a scale curvature, and they are denoted by Ki. Okay. Yeah, now we present one of the main findings of our work, which is the Darboux vector. We use a slightly different version from Heston's, more suitable for power system, where the velocity is included in this vector. It has some properties shown here, and analyzing in detail the Darboux vector and its blades, we found that there is it's advisable to separate them into two blades, omega I. We will see later that the omega 1 has a relevance in our investigations. So this first omega 1 is called the grid angular velocity blade and has a special relevance, satisfying these interesting properties. So some examples are provided here. The first one is a multi-phase balanced sinusoidal signal. This is the equation for every phase. So the representation, yes, the three phases, the three voltages are equal in amplitude, and they have a phase delays of 120 degrees. So by building the voltage vector in this way, we end up with a linear combination of vectors A and B. These vectors A and B are represented here. So the signal describes a perfect circle, as we will show later on. So these are, I will move on quickly. So these are self-derivation for this special system. It's very important to note that in this case, the curvature, the scale curvature K1 is exactly the angular frequency of the system, exactly the same. So based on the GA4 library, here we present the result. We will find a perfect circle with a constant curvature K1. And of course, because the curve lies in a plane, there is no second curvature coefficient. The second example is an imbalance multi-phase signal. In this case, every amplitude is different, and also the phase delay between the signal can be also different. Here we show for comparison purposes with the balance system. And here we show the voltage vector, and now A and B is a bit different from the balance case. The relevant numbers are here. So now the curvature K1 is not constant, it varies with time, and also the omega 1. So we can see in this animation how now the curve describes, of course, an ellipse in a plane, and the first curvature coefficient is now varying on the top left, on the top right, the second window. We can see how the curvature is varying with time. We also see the Frenet-Serret frame attached to the curve and how it moves with time. And just another one, just to finish, a very important signal, which is present in model system, a possible harmonic pollute signal. You can find here some harmonics. Yes, harmonic of order 2 and harmonic of order 7. These are the results we found, and this is the representation. Now the curve has a different shape, it evolves in time with this strange shape, but it's still contained in a plane. So the second curvature is different. So this final case is a real signal we measure in a low voltage panel in our laboratory in the University of Almeria. So as you can see, it's very near to a circle. It's almost balanced. So the second curvature coefficient is almost 0, but you have some variation because of the noise. So in this way, you can interpret the frequency of the whole system by studying as it was rigid motion body. So the last one, this is another measurement in another place. In this case, we have harmonics. The shape is not circular, but something like hexagon or something like that. You can see the green circle, which is the omega bivector representing the geometric frequency. So I end with my conclusion. So the generalization of the concept of geometric frequency applied to multiphase systems. Applying geometric algebra and differential geometry, we can found the invariants associated to these systems. And the key here is to employ the Darboux bivector to extend to n-dimension system. So it has potential benefits for the voltage stability and frequency analysis in arterial system. So thank you very much.
Yeah. Yes.
Thank you. That looked really interesting. I don't know much about multiphase signals, but I have many colleagues who deal totally with multiphase signals. So my question is, if I went back to talk to my colleagues in Cambridge who work on this, would they, how much of this would they know? Would they know about the electrical curves and the frames going round? And can you just do it in a nicer way? Or do they not use these?
What do you mean with a nice way?
Well, with your bivector, etc., and get nice, because they potentially could do this conventionally with mathematics. So which bits of it would they know about?
But it's already done with mathematics inside. Yeah. So the GA full library performs all the computations. And this kind of visualization is just a plugin that Professor Aid created for visualization purposes, but for the engineer. Do you know the difference between a mathematician or physicist and an engineer? We want to visualize everything.
Of course.
We need some kind of visualization to understand or for a better understanding. So the visualization is just an additional tool, but all the computation are performed by a mathematical library.
Okay, so they could find this sort of thing useful.
Yeah,
and they would understand it all.
There are Professor Milano, with which he created the concept of geometrical frequency. It's already used in population, some papers, and he's now proving that a better control, a better frequency control, can be done. Can be shown to all the colleagues instead of using three separate, for three-phase systems.
Okay.
Three separate controls. So what is the main control? There's phase R, phase S, phase T. I don't know. So you join all the information. So you get all the information. Like I think we all know that by mixing some kind of multivector, but in this case, this is not a multivector. It's a vector, and you get more useful information.
I assume that three-phase systems are the most common.
Yeah. This is the most common, but
useful.
Right now, more phases are becoming useful. For example, for wind generator application, for offshore wind generator application, for electric vehicles traction, for train traction, for a lot of things, because they are more reliable than three-phase systems. But for transmission grids, okay, the three-phase system is the more
Okay.
well used.
Thank you.
Okay. Maybe by alt tab.
Okay, there we go.
Can I write that?
David, is there any chance you can read off the question? I'm having difficulty.
Here, or is-
Should be this guy here.
Maybe you need to stop the screen share or something like that.
Yeah, please.
Sorry?
But, and I usually measure the algorithm to say that in this group is like. But I'm not familiar with the, how do you say this? The dipole bivectors. We've been working in this stuff for about 10 years. I've never heard that. I found one research paper just while we're talking. Would someone just quickly tell me what that is? I've just never heard that before. And why is it unique for these? I mean, it's all in applications in power, this particular bivector.
Sorry, what? What's your question? What's your question, sir?
What is this? You're going through the explanation, your presentation, and I followed it up until the dipole bivector. What is that? Where'd that come from?
The bivector.
Well, that particular bivector, what makes it unique?
Darboux bivector.
Yes.
Well, it's a well-known concept in traditional differential geometry.
Yes, I
They
do
call-
see those vectors.
They call Darboux vector,
Yes.
but because of the application of geometric algebra by David Hastings, it's you can understand for high-dimensional systems. You can understand the rotation of this rigid motion as a bivector. So we already know that rotation in n-dimensional space is a bivector. So we use that.
Taken that vector and moved it over to the GA domain.
Yeah.
Okay. I'm just,
Very easy.
yeah, okay, very simple.
If the next step of Frenet equations, you also consider torsion.
Sorry?
If you go to the next level of Frenet equations, you also have a torsion, including the acceleration.
No.
And the torsion in geometric algebra is a free vector, which describes the volume, how much the curve goes out of the plane.
No, only we study only using the concept of bivector. With this information, we have enough to understand the invariance of the curves.
So the torsion is not of relevance for you.
Sorry?
So the torsion trivector
Yeah.
is not of relevance.
We have first curvature coefficient, which is known as a curvature. Second curvature coefficient, which is known as a torsion
You call it-
in three dimensions. But when you move to more dimensions, there is no more names. So we say first curvature, second curvature, and so on. But yes, the second curvature coefficient is what is known as traditionally as a torsion of a system. So for three-phase systems, very easy. Curvature and torsion. But if you have a 6-phase system or a 24 system, like in for example, a ship, you need to put all the names. So yes, first, second, third, so on.
Yes, thank you. We are very late, so the speaker answered the other question in personal in the chat. Thank you very much.